There is a fundamental principle in orbital mechanics that has been tested and verified thousands of times across centuries of astronomical observation. An object in motion remains in motion unless acted upon by an external force. For objects in space, that external force is gravity. The sun pulls, planets pull, the object responds according to Newton's laws with mathematical precision. You can predict where any object will be at any future time if you know its current position, velocity, and the gravitational forces acting on it. The predictions are not approximate. They are exact to extraordinary decimal places, until an object changes course. And 3I Atlas has changed course 3 times since entering our solar system in July 2025. Not random perturbations, not measurement errors, not orbital variations within predicted parameters. Deliberate course corrections that altered its trajectory in ways that gravity alone cannot explain. Let me take you through each course change chronologically, showing you the exact measurements, the timing of each maneuver, and what the modifications achieved. By the end, you will understand why these trajectory adjustments cannot be explained through natural processes and what they tell us about the capabilities of this object. The baseline, what we expected. When 3I Atlas was discovered on July 1, 2025, astronomers immediately calculated its orbit using standard astrometric measurements. Multiple observations over several nights provided position data. From those positions, you can calculate velocity and trajectory using well-established mathematical methods that have been refined over centuries. The initial orbital calculation showed a hyperbolic trajectory with an eccentricity of approximately 6.1. Eccentricity measures how elliptical an orbit is. A circle has eccentricity 0. Earth's orbit is nearly circular with eccentricity 0.017. Highly elliptical orbits have eccentricities approaching but less than 1. Hyperbolic trajectories have eccentricities greater than 1. This means the object is not bound to the sun. It entered from interstellar space. It will swing around the sun once and depart back into interstellar space. It will never return. The predicted perihelion, closest approach to the sun, was calculated at approximately 1.4 astronomical units, occurring on October 29, 2025. After perihelion, the object would continue outward, passing relatively close to Jupiter's orbit before departing the solar system entirely. All of this was standard gravitational dynamics. No surprises, no anomalies. But then the object started deviating from predictions. Course change 1. The initial detection, August 2025. By mid-August, after 6 weeks of continuous tracking, astronomers noticed something unusual. The position of 3I Atlas was not matching the purely gravitational predictions. The discrepancy was small, measured in arcseconds on the sky, but it was real and statistically significant. Davide Farnocchia, a navigation engineer at NASA's Jet Propulsion Laboratory who specializes in orbit determination, analyzed the accumulated astrometric data and concluded that 3I Atlas was exhibiting non-gravitational acceleration. Non-gravitational acceleration means the object is accelerating in ways that cannot be explained by the gravitational forces of the sun and planets alone. For comets, this is common. Outgassing produces jets of vapor that act like tiny rocket engines, slightly altering the trajectory. We see this behavior routinely. But 3I Atlas was not showing typical cometary activity at that time. It was still beyond 3 astronomical units from the sun. Water ice does not sublimate significantly at that distance. The object should have been largely dormant. yet it was accelerating. The magnitude of the acceleration was measured at approximately 1.1 times 10 to the minus 6 astronomical units per day squared in the radial direction, meaning directly away from the Sun. There was also a transverse component, acceleration perpendicular to the Sun direction, measured at 3.7 times 10 to the minus 7 astronomical units per day squared. These numbers are small in absolute terms. We are talking about tiny changes in velocity accumulating slowly over weeks. But they are large enough to significantly alter where the object will be months later. Think of it like steering a ship. A small change in heading maintained for hours will result in arriving at a completely different port than originally planned. The course change detected in August was the navigational equivalent of adjusting the heading slightly but deliberately. Professor Avi Loeb from Harvard analyzed these measurements and calculated what they implied about the object's trajectory. Without that acceleration, 3I Atlas would have passed Jupiter at a significantly different distance than it now appeared headed for. The acceleration was steering the object toward a very specific target. Course change 2. Perihelion maneuver, October 29, 2025. The second and most dramatic course change occurred at perihelion on October 29, 2025. This is exactly when you would expect maximum cometary activity due to intense solar heating. It is also, critically, the optimal moment for any spacecraft to perform trajectory adjustments. At perihelion, you are deep in the Sun's gravitational well, moving at maximum velocity. Any thrust you apply gets amplified by the Oberth effect, a fundamental principle in orbital mechanics where propulsive maneuvers performed at high velocity produce greater changes in orbital energy than the same maneuvers performed at low velocity. If you were designing an interstellar probe and wanted to adjust your trajectory through a stellar system, you would plan your major maneuvers to occur at perihelion to maximize efficiency. That is exactly when 3I Atlas performed its largest course correction. During the perihelion passage, which occurred when the object was hidden from Earth-based telescopes behind the Sun's glare, the non-gravitational acceleration increased dramatically. Post-perihelion observations, once 3I Atlas emerged back into view in November, showed that the trajectory had been altered significantly. The object had lost substantial mass. Analysis by Loeb and colleagues estimated that 3I Atlas shed approximately 13% of its total mass during the perihelion passage. Losing 13% of your mass in a matter of weeks is extraordinary even for comets. But more important than the mass loss itself was what that mass loss did to the trajectory. The acceleration profile during perihelion, as reconstructed from post-perihelion orbital tracking, was not uniform or random. It was focused and directional. The jets producing the acceleration were not firing equally in all directions, as you would expect from chaotic sublimation of randomly distributed ice deposits. They were producing thrust in specific directions that adjusted the trajectory in specific ways, and the adjustment achieved something remarkable. Before the perihelion maneuver, based on the July and August trajectory data, 3I Atlas was predicted to pass Jupiter at a distance of approximately 54 to 55 million kilometers. After the perihelion maneuver, the new trajectory calculations showed the object would pass Jupiter at 53.4 million kilometers. That is Jupiter's Hill radius. The exact boundary where Jupiter's gravitational influence equals the Sun's gravitational influence. The probability that random outgassing would adjust the trajectory to target this specific, mathematically significant distance is extraordinarily low. It would be like throwing a dart while blindfolded and hitting the bullseye. Once is luck, but when the dart lands exactly where it would need to land to achieve a specific goal, you start questioning whether the throw was truly random. Course Change 3. Post-perihelion Fine-Tuning, November 2025. The third course change was detected in November and early December, as continued tracking of 3I Atlas showed additional small deviations from the post-perihelion predicted trajectory. These adjustments were smaller in magnitude than the perihelion maneuver, but were still measurable and significant. Dan Green from the Center for Astrophysics at Harvard and Smithsonian stated publicly that they were carefully analyzing whether small non-gravitational forces were still acting on the object as it moved outward from the Sun. By late November, NASA's updated orbital calculations confirmed that additional course corrections had indeed occurred. The trajectory was being continuously refined. The predicted Jupiter encounter distance was updated multiple times as new data came in. Initial post-perihelion calculations showed 53.587 million kilometers. Later refinements brought it to 53.445 million kilometers. Each update brought the predicted distance closer to Jupiter's Hill radius of 53.502 million kilometers. This progressive refinement is exactly what you would see if an object with active guidance systems was making continuous small adjustments to maintain precise trajectory control. It is not what you see from passive objects following purely gravitational paths with random comet outgassing adding noise to the trajectory. Professor Loeb noted that the timing and magnitude of these adjustments suggested fine-tuning. The object was not just heading approximately toward the Hill radius. It was actively steering to hit that target with precision. Why these course changes matter? Let me explain why these three trajectory modifications are so significant and why they cannot be easily explained through natural comet behavior. First, the timing. The major maneuver occurred at perihelion, which is the single most efficient location for trajectory adjustments. If you were managing fuel and wanted to get maximum effect from minimal thrust, you would plan your burns for perihelion. Natural outgassing is driven by solar heating, so yes, maximum activity occurs near perihelion. But natural processes do not understand orbital mechanics and efficiency. They do not time their maximum output to coincide with the moment of maximum orbital efficiency. That requires planning and intent. Second, the directionality. Random outgassing produces thrust in random directions based on where ice happens to be and where sunlight happens to strike. The net effect on trajectory is usually small and somewhat unpredictable. But the course changes observed in 3I Atlas were not random. They consistently pushed the trajectory toward a specific target. Each correction brought the Jupiter encounter closer to the Hill radius. That is not random walk. That is guided navigation. Third, the precision. The Hill radius of Jupiter is 53.5 million kilometers. The current predicted encounter distance is 53.4 million kilometers. That is precision to within 0.1%. For comparison, NASA's Juno mission, which was designed with careful trajectory planning and multiple course corrections during its 5-year journey to Jupiter, achieved Jupiter orbit insertion with similar levels of precision. We are seeing spacecraft-level navigation accuracy in an object that is supposedly a natural comet. The natural explanation and its problems. In November 2025, a research paper by Florian Neuckart attempted to explain the non-gravitational acceleration of 3I Atlas through conventional volatile-driven outgassing. The paper modeled carbon monoxide and carbon dioxide sublimation using thermophysical equations and argued that the observed acceleration could be reproduced with realistic assumptions about active surface areas and jet collimation. This is a serious scientific paper making good faith efforts to explain the observations naturally. But there are problems with the natural explanation when you examine it carefully. First, the model requires very specific assumptions about surface composition, active area fraction, and jet directionality to match the observed acceleration. You need carbon monoxide to be concentrated in specific locations. You need those locations to be arranged such that the jets they produce happen to thrust in directions that move the trajectory toward the Hill radius. You need the activity to ramp up at exactly the right times. Each assumption individually is plausible, but the combination of all assumptions needed simultaneously becomes increasingly unlikely. Second, the natural model does not explain why the trajectory refinements continued after perihelion when solar heating was decreasing and natural outgassing should have been declining. If the course corrections were driven purely by solar heating, they should have peaked at perihelion and then rapidly decreased as the object moved outward. Instead, we see continued small adjustments weeks after perihelion, suggesting active rather than passive control. Third, and most critically, the natural model does not address the target. Even if conventional outgassing can produce the measured magnitude of acceleration, that does not explain why that acceleration happened to move the trajectory toward the mathematically significant Hill radius. The natural explanation accounts for how much thrust was produced, but not why that thrust steered toward a specific goal. It is like explaining how a car engine produces horsepower without explaining why the car drove to a specific address. What the course changes achieved. Let me be explicit about what these three trajectory modifications accomplished. They took an object that was initially on a path that would pass Jupiter at approximately 55 million kilometers and adjusted that path to pass at 53.5 million kilometers instead. A 2 million kilometer adjustment might not sound like much on solar system scales, but it is the difference between passing outside Jupiter's gravitational sphere of influence and passing exactly at the boundary of that sphere. At the Hill radius, an object is balanced between Jupiter's gravity and the Sun's gravity. If you have propulsion capability, that is the ideal position for orbital insertion. You can fire engines to enter Jupiter orbit with minimal fuel expenditure. If you wanted to deploy satellites or probes into Jupiter orbit, targeting the Hill radius would be the optimal approach trajectory. It gives you maximum flexibility. You can commit to orbit insertion, or you can continue past if conditions are not favorable or if you detect something unexpected. The course changes move 3I Atlas from a trajectory that had no special significance to a trajectory that targets the single most important point for potential interaction with Jupiter. That is not coincidence. That is navigation. The March 16 test. 22 days from now, on March 16, 2026, 3I Atlas will reach Perigove, its closest approach to Jupiter. Every major telescope on Earth and in space will be watching. If the object passes at the predicted 53.4 million kilometers, that confirms the trajectory calculations and shows that the course corrections achieve their apparent goal of Hill radius targeting. If it passes at a different distance, that would indicate additional course corrections occurred during the final approach that we have not yet detected. And if the object does anything other than simply pass by, if it releases something, if it changes velocity in ways that indicate orbit insertion, if it performs any maneuver that demonstrates active control, then the question of natural versus artificial origin will be definitively answered. The trajectory data alone already suggests artificial origin strongly. The three documented course changes, their timing, their directionality, and their achievement of hill radius targeting are all consistent with guided navigation. But the March 16th encounter will provide the final test. Because an object that can change course 3 times to target a specific gravitational boundary can certainly change course a 4th time to demonstrate capabilities we have not yet seen. We are 22 days away from that demonstration. Watch what happens at Jupiter. Because if 3I Atlas performs any additional maneuvers during the encounter, if the trajectory changes in any way that cannot be explained by Jupiter's gravitational influence alone, then we will have proof beyond any possible doubt. Proof that we are watching active guidance. Proof that these course changes were intentional. Proof that something with propulsion and navigation capability has entered our solar system from interstellar space. The 3 course changes we have already documented point strongly toward that conclusion. The 4th course change, if it occurs, will confirm it absolutely. March 16th, the day we find out whether 3I Atlas is just passing through, or whether it has other plans.